Let's look at a very specific example of rotation. Come on. There we go. Aha. That makes sense. So this thing is just giving me trouble. There we go. So let's look at a simple object rotating. Now I'm going to draw, let's say we've got something looking like this. So this is a rod, a rigid rod, but it has negligible mass. To its end I tie a mass, let's call that M1. To its other end I fix a mass which I'm going to call M2. Let's say over here we've got another rod which is slightly shorter. To that I fix a mass M3, and over here I've got a mass M4. So it's almost like we take two steel rods, fix them, they form a cross. The cross is not symmetric, so all those four little spokes are not equal length. And I put four different blobs of mass at every end of this rod. And let's say I now fix this rod so that it can turn around this point. So this whole rod can now rotate around this point over here. So this whole thing rotates, let's say, in a counterclockwise direction around that point. So let's just refresh what we did yesterday. So let's say this rod rotates through a certain angle. So let's say it ends up somewhere over here, something like that, and something like that. So this mass has moved along an arc and is now over there. This mass has moved along an arc, it's now over there. Same for this one, it's now over there. Same for this one, it ends up over there. So the cross has rotated through, so this spoke has rotated to there through an angle theta. This spoke has rotated from there to there through an angle theta. This spoke has rotated from there to there, again through an angle theta, and this spoke has rotated from there to there, again through an angle theta. Right, so this is how this cross of four masses is rotating. Now let's try to look at just the speeds of these masses. So let's call this length, so from there to there, I'm just going to call length 1. From there to there, I'm going to call that length 3. From there to there, I'm going to call length 2. From there to there, I'm going to call length 4. Right, so L1, 2, 3, and 4 just tells me how far away mass 1, 2, 3, and 4 is from my center of rotation. So if we look, for example, at the speed, not the angular speed, just the regular old speed of mass 1, so of this mass, let's say the cross was, as I drew it, at some point time was 0, and it rotated through an angle theta at some time t final. So the speed of mass 1 is just equals to the distance it travels divided by the time taken. The distance it travels is this length of arc. It starts over there and it travels all the way around to there. So let's call that arc length S1. So this in our case will be equals to the arc length S1, so it's a path on a circumference of a circle with radius L1 that this mass travels, and it travels that in a time
T final minus T initial. T initial will be 0. So we can simply write it as S1 divided by T final. That would give me the average speed of its mass. Now, so this will be it for mass 1. If we look at, for example, mass 2, the speed of mass 2, so that one over there, it travels this length of arc, so let's call that S2. Now you can see already S2 is shorter than S1, so that little bit of arc is shorter than that little bit of arc. So this will be S2 divided by the same amount of time. Right, you can go and measure this out with a little piece of string, but because as it's drawn here, this length L1 is greater than L2, that means the arc over here that through which mass 1 travels is a longer distance than the arc through which the second mass travels. So let's just give, just to be consistent, let's give this speed 1. And from this, because S1 is larger than S2, so that arc is larger than that piece of arc, we have that the speed of mass 1 is greater than the speed of mass 2. Right, so we can figure out the speeds of all these masses in 1, in 2, in 3, in 4, and if they're all not at the same distance from the center of rotation, they will have different values. So when I rotate an object, depending on how far away I am from the center of rotation, parts of the object will have different speeds relative to other parts of the object, which might be closer or further away from the center of rotation. However, we know we can write this in a slightly better form. We know that a full circumference of a circle is equals to 2 pi times its radius. And we can basically then say that 2 pi is equals to the circumference divided by the radius. And we can generalize this now to define an angle in radians. We can say an angle in radians, so it's a different unit than degrees, is equals to some arc length divided by a radius. So if this becomes the full circumference, so if the arc length is equals to the circumference, then theta is equals to 2 pi radians. So from this definition of the circumference of a circle, we can define a new way to measure angles. An angle, so let's say that's the radius, and here is my arc length S. Then we say the magnitude of this angle in radians is equals to however many meters that is divided by however many meters that is. Right, so we use now arc length and radius to define an angle. Right, that's what we did yesterday, and that angle is just called a radian. Now, from this, we can rewrite our expressions for the speeds of mass 1 and mass 2. So is there any questions regarding this? Okay, I know it's a new definition, but just remember this idea of the circumference of a circle, and that we can now use the ratio of circumference and radius, or a little section of the circumference divided by radius, to define an angle. So if we look at our speeds, I can, for example, write that the speed of mass 1, which we said is equals to arc length 1 divided by T final. This I can write, this arc length will be equals to that times this angle theta. So that it will be the radius times our angle theta divided by time. Now that angle theta is actually a change in angle because it started over here. You could say its angle with the horizontal was 0. It ends up over there. So its angle changed by that amount. So we can simply write this then as a new quantity called L1 omega. And omega now is called the angular speed. And this is equals to a change in angle divided by the change in time. And you can do the same for the speed of mass 2. This will be equals to how far it is away from the axis of rotation times the angle through which it has been rotated divided by T final. So this will be L2 times omega. So we see that two different masses at two different distances away from a point of rotation have the same angular speed. So although their tangential speed, so distance traveled divided by time, becomes greater the farther away you are from the axis of rotation, if we work in terms of these angles that have been swept out as this thing rotates, we find a quantity that's the same for both, and that is equals to omega, which is equals to the angle through which this thing rotated divided by the time it took to do that rotation. So now we've got two ways we can describe the system. We can either go and figure out the speed of each individual particle and work with that, or we can say, well, we can work with purely angular quantities because we know things like angular speed will be the same for every particle or every point on this rotating object. And we can easily then also convert between regular or tangential speeds and angular speed. So in general, we've got that the angular speed is equals to the tangential speed divided by the distance away from the point of rotation. So this is just the regular tangential speed. This is just distance divided by time. And this is how far from axis of rotation. And this quantity is just equals to the angle swept out in a certain amount of time. So that's the angular speed. Now remember, yesterday I asked you, when we looked at rotation, there's this idea that if an object rotates, parts of it that are further away from the point of rotation have got a greater speed. I asked you, how would we calculate, for example, the kinetic energy of this object? Because we know kinetic energy is a half mv squared, but now different parts of my object has got different values for the velocity. So which one do I use? Do I average over the whole thing? Do I somehow break it up into little parts and calculate the kinetic energy for every single one? How do we do it? Well, if we look again at this cross that we had, so there was mass M1, there was mass M2, mass M3, mass M4, right? And this one has, at this instant, got a tangential speed V1, this one has got a tangential speed V2, V3, This one has got a tangential speed v2. This one has got a tangential speed v4. And if we assume that these masses are point-like, so they're pretty much as small as they can be, and we assume the rods have got no mass, so rods have no mass, so it's a very light material that we use, then we can say, well, each one of these masses by itself has got a kinetic energy. So we can say the total kinetic energy of this rod, of this cross, is equals to the kinetic energy associated with mass 1 plus the kinetic energy associated with mass 2 plus the kinetic energy associated with mass 3 plus the kinetic energy associated with mass 4. Now, these expressions we know, this is just a half times mass 1 times its speed squared. This is now its tangential speed, so that the speed that we get by looking at the physical distance traveled divided by the time it takes. And the same for the other ones. And we can actually write this in a slightly simpler way. We know that there is this link between a tangential speed and an angular speed. So we can substitute that in there for every one of these masses. So we're going to sub in that V is equals to omega times distance, where from there to there is now, we're going to call this distance R1, that we're going to call distance R2, that we're going to call distance that's R3, that's R2, that's R4. So if I know the speed and I know how far this object is from the point of rotation, I can calculate its angular speed. So I can substitute that into our expression for the kinetic energy. So you get this is equals to a half m1 times r1 omega squared plus a half m2 r2 omega squared plus a half m3 r3 omega squared plus a half m4 r4 omega squared. The reason I'm doing this is I know omega is the same for m1, m2, m3, m4, because what is omega? Omega is the angle through which an object rotates in a certain time. And as I showed you over there, if this cross rotates like that, this beam rotates through an angle theta, which means those two must be the same. This beam rotates through an angle theta, which means those two must be the same, because the angle that the cross beams make with themselves remain 90 degrees, all four of those angles must be the same. So every mass rotates through the same angle in the same amount of time, which means every mass has got the same angular speed. So we can write this kinetic energy in a simpler form. We can say it's equals to a half. Now I'm going to write shorthand. This just means the sum of, starting from I equals 1 all the way to I equals 4. So if you write this out, you get m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. So that's what this means. It's just a shorthand way to say I must sum terms of this form
starting from 1, ending up at 4.
Yes. Oh yeah, the omega must be squared as well, obviously. Sorry. Now, this thing that I've drawn here, or this thing in this rectangle, we give this a special name. We call this the moment of inertia. Now, what does the moment of inertia tell you? It's a measure of how mass is distributed around the axis of rotation. And it's something that you can typically calculate. If you've calculated once, you basically know what it's going to be, unless the mass distribution changes. But if I know how many masses I've got, if I know how far every single one of them is going to be from my axis of rotation, I can calculate the moment of inertia once, and then for all crosses looking like this, I know what the moment of inertia is going to be. So we write this as a shorthand. We say this is then equals to a half I, where I now denotes the moment of inertia. So I is equals to this times omega squared. So this then gives me the kinetic energy of a rotating object. If I know its moment of inertia, it's almost the same as knowing the mass of an object, but moment of inertia contains more information. It's not just total mass, it's how every mass is distributed around an axis of rotation. So if you know the geometry of your object, you know through which axis it's going to rotate, and you know how the mass is distributed, you can calculate the moment of inertia. And you'll see it's even more general than that. For different types of objects, so all cylinders have got a similar moment of inertia. All rectangles have got a similar moment of inertia. So if you've calculated it for a certain type of object, like a sphere, a cylinder, a hoop, a rectangle, or a square, a cube, you've done it. So it's not something you have to do every time. And we're going to do a few calculations more to make you comfortable with the idea of a moment of inertia. But most often, we're going to give you a table saying, well, cylinders have got this moment of inertia. Rectangles have got this moment of inertia. So it's really something you can most of the time look at in the table. Because if you know the geometry of the object, if you know how mass is distributed, you can calculate the moment of inertia once, and then you don't have to ever do it again.